We are recording as of right now. So I'm going to go ahead and share my screen and just do my little intro, and then I'm handing it off right off to Bob up here. He's going to be doing the training from Prominent. So let me do my little intro since I put this together, asked him to be here. All right, so welcome to this month's training. It's another ORP training from a different provider, specifically with Prominent Controllers, brought to you by Space Coast Pool School. This is Facebook Live, and the recording will be available on the YouTube channel for Space Coast Pool School. If you're not able to make the live training today, I understand a lot of people are out in the field working depending on time zones. So you can still watch the training, and then we'll make sure you have contact info for the people from Prominent so that you can email them, call them if you're dealing with their controllers, so that you can ask them any specific questions. A little bit about me, who's the host of the class and put it together. I'm Lauren Broom with Space Coast Pool School. I am a provider of the Pool and Hot Tub Alliance Certified Pool Operator course. I teach in person in Florida, but I offer 100% virtual online certified pool operator courses to anybody from anywhere. You can go to my website at spacecoastpoolschool.com for more information, or call me at 321-726-8509. My number is there. I do private classes as well virtually. If you have a group of like 5 or 6 or more, I'll teach a private full two-day class, or a fusion class, which is the 8-hour self-paced course with the full 1 day on Zoom. Includes test time as well. So I can work with you. Just contact me. We'll figure out what's the best way for you, private class or a class on my website that I call a public class. So I want to welcome our main presenter today, Robert Capel with Prominent Fluid Controls. Thank you very much for being here today, Bob. And I'm going to go hand it off to you. And if there's anything else you want to introduce yourself with, title wise or anything else, I'm going to let you do that. Thank you very much for being here today, Bob. I always have a lot of questions about ORP, and I know a lot of people either listening to the recording or live are going to have some questions as well.
Well, thank you, Lauren, and it's great to be here. And I really do appreciate the opportunity to get in front of some of these folks to go ahead and talk about ORP. It's one of the more interesting and confusing topics in aquatics. Quite frequently, people have questions about it, and even after taking a class, they still have questions and can't fully grasp what ORP is. So hopefully after today, going through some of the basics, trying to put it into some good perspective, the folks, when they leave here, will have a better idea and have some of their questions answered as to what ORP is and how it works in the pool. One of the things I like to do before I get into the actual instruction here, or the topic presentation, one of the things I really, it's really important for me to do is not to turn this into a sales seminar. I'm really a big advocate for aquatics. The last 25 years I've been immersed in aquatics, all the way from tying rebar in shells, getting ready to have gunite put on, plastering, all the way to building the pools, to maintaining the pools, to being the pool guy on the deck, doing my wet tests daily, winterizing pools, reaching in the skimmers and pulling out dead frogs as I'm trying to get the winterizing plugs out of them. And I spent a lot of time as a service manager at a pool construction company and large facility startup guy. And then I eventually worked my way into the sales roles with Stranco, US Filter, Siemens, and now Prominent. So I've run the gamut. I've been at the grassroots doing the hard work in the field that all these folks do. And then I've also understand the manufacturing side of things. So I'm excited to bring kind of a very broad perspective and a broad range of ideas into this. So one of the things I'd like to do before we get started too, is I like building parking lots. So does everybody have the capability to chime in with questions right now, Lauren?
I think they can, so everybody
Just
that's
unmute.
on this live can either unmute themselves if you have a question, or you can use the chat window, which
Mhm.
there should be a chat window, ability to chat, get to the chat window and ask a question through that as well.
What I'd like to do right off the bat is, by building the parking lot, I want to hear what your questions are right up front so that I can integrate that into my discussions as we move along. The other last thing I don't want to do is just regurgitate all this information and then I'm not hitting on the topics that are important for you to come away answered after this presentation. So if anybody has anything right now, please chime in. I'll get that written down and I'll make sure I hit those topics during the presentation.
Any specific questions from anybody actually in the Zoom room right now that you want him to cover? Somebody, Nick, said, why does ORP go up at night? Thank you, Nick.
Anybody else? That's an interesting one.
All right, I'd
guess,
say we are
okay,
good. You get to
we are
start.
good. We will roll right through this then. So I need to share my screen right now,
Yes.
Lauren?
Yep.
Okay. And looking for that tab again.
Here's.
There we go. Okay. Bear with me. Can everybody see my screen?
I can see your screen.
Okay, very good. So first of all, I really want to go ahead and set the plate of what the purpose of the process and the payoff is going to be for the presentation. So today, coming out of here, we're going to talk about what our ORP is in detail, how ORP is used in aquatics, how ORP relates to the water parameters, some of the other measurements that we take in the pool, specifically pH, and then how we can open up a little bit of discussion how you can utilize ORP to maximize your advantage, to why you're using it and how you're using it. One of the things I'm going to plant the seed right now, and then I'll return to this later on in the presentation, is that an ORP controller does not control part per million content of the water. It controls ORP. So let's leave that right there and it'll become more evident what I mean by that as we go through the presentation. So let's give ORP a name right off the bat here. I think it's really important to understand what ORP means. And you've heard it, you have heard oxidation reduction potential, ORP. Some people say ORP, and there's another group of people, especially in Europe, overseas, that'll call it redox, which is reduction oxidation. And then there's also a brand name that was given back in the 80s by one manufacturer called HRR, which is high resolution redox. So it's just taken the European word and blended it into some marketing content to make it seem like they had something better than everybody else at that point in time. This was before PPM controllers were actually viable for the aquatics industry. So everyone was competing to prove that they had the best ORP controller. But suffice it to say, ORP is ORP. There's no way to sense it better or worse. You're just going to sense it. And we'll talk about exactly what that means in a moment here. So moving forward, we need to give it a place. ORP has been around a long, long time. It's nothing new. In fact, I did a little bit of research coming into this presentation because I always like to put things in the historical perspective. And ORP was first discussed as a scientific principle back in 1697. And it was by a chemist named Stahl in Germany, who was burning charcoal. And he realized that when he burnt the charcoal changed form and it gave off light and heat. And he said, there's a process occurring here where there's a chemical reaction being caused by this fire. And fire, all fire is very rapid oxidation. So we're changing the state of a material, and fire is the catalyst for that change of state. So that change of state is one of the processes is called oxidation. So oxidation is simply when an atom of any compound loses electrons due to a chemical reaction. And that chemical compound changes with the loss of that electron. And so you can think of it as oxidation is losing. Okay, so you can see by my little graphic here is that we have an electron coming off. It's changing state by loss of the electron. And in pools, oxidation supplements filtration. So we can tell this because our filters only capture certain debris to a certain size, whether it be a diatomaceous earth filter, it could be a sand filter, it could be a cartridge filter with paper pleats in it. There's a host of different type of filtration types, but they only go down to a certain micron. So in the pool, we're using chlorine to oxidate all the smaller things. And we're not even talking about sanitation right now. All we're simply doing is just talking about the oxidation that's occurring. So what we're doing is we're basically burning up or we're breaking down those finer particles that aren't filtered. Because if we don't have chlorine in the pool, even if we have really good filtration, the pool still could be cloudy just to very small particles that are in the water that cannot be captured by the filter process. So this is the first part of ORP, oxidation. The other side of the ORP acronym is reduction. So reduction is gaining electrons in a chemical reaction. So we can look at this side of this is when electrons that are coming off something that's being oxidized will be gained by something being reduced.
I don't mean to interrupt you, Bob, but I think we're still, I'm on an old slide. I don't know about everybody else. Do you guys still on the slide where it says first, let's give it a name?
Yeah.
Now yeah,
okay.
the slides weren't switching.
Okay, is it better now?
Yeah.
Okay, so thank you. I made a mistake by going ahead and just switching my screens from one monitor to the other. And apparently,
I didn't mean to interrupt you. I just
but thank you.
tell that you had moved on and we were still on the other slide. And I know some people like to see the actual like visual part of it too. So
sure. So I'll just give this a moment here. I'll forward giving it a name with oxidation reduction potential, ORP, redox, HRR. I'm going backwards. So oxidation here is, so when we lose an electron, as by this graphic over here, we can see we have an electron coming off. Reduction is gaining. So what's coming off of something being oxidized is being gained by something being reduced. And we don't really need to dive into this, but I just want to give you a little background of what the acronym ORP means. So we have O for oxidation, then we have R for reduction. So something being reduced is going to gain an electron. It's just a change of chemical composition. And as far as pools go, if you remember, I was talking about oxidation here, where the oxidation supplements the filtration in a pool. The reduction, we really don't need to think about that at least at this point in time of the importance in the pool, except for what I'm going to talk about next. And this is one of the main points I'd like to drive home. P for potential. So we have oxidation, reduction, potential. And the word potential is almost everything in those first two acronyms. What is potential? It's just what it means. It means the pent-up capability of making something happen. So for instance, if I say that somebody tells me I have great potential to earn money, that means I have this built-up ability to make it. I'm not making it yet, but I have it kind of held back and I have this potential to make that happen. Or you can think of water being held in a high dam that's being allowed to go through sluice gates in a hydroelectric dam. So the potential of us to be able to generate electricity is this buildup of water in the lake behind the dam. And so there's an awful lot of potential if that dam is high, if the water level is high in that reservoir, to come through there. Now, if the reservoir is almost empty, my potential to turn those turbines is very low. So the more water, the more potential I have, the greater potential I have to create changes. Now, what's very cool about this whole thing is that this potential, this built up capability of making something happen in water due to ORP, can be measured in a millivolt reading in the water. And so basically, the higher the millivolts in the water, the more potential we have. The lower the millivolts in the water, the less potential we have. And what is that potential? The potential basically to oxidize things that we want out of the water. That oxidation process can be for oxidizing contaminants in the water, organic contaminants, or it can be for disinfection. So again, the higher the millivolt reading in the water, the greater potential we have to do this do the things we want to see happen in pool water, which is sanitizing and also oxidizing. So at this point, what I want to do is pause for a moment, because that's a lot in a very short amount of time. So I want to stop and see if there's any questions by anybody right now over the content that we just covered. We have a lot more to go through, but I just want to kind of take a little break here and see if there's any questions anybody has.
So anybody have any questions for him? Come off of mute or use the chat window.
And I know we have some savvy people on board here, so this might be a little basic for y'all. So.
And certainly if anybody has anything to add or anything like that, please add to our story, our training here, so we can have some relevant experience with the controller out in the field or anything like that.
And again, this is a point too. I may be showing pictures of certain things that are our equipment, but it's really against my nature to go ahead and talk about the specifics of my controller. What I will talk about is that ORP controllers all share similar technology, and with the way they sense through the sensor and through the way they read. Beyond that, there's certain subtleties with other capabilities with the controller, but it doesn't have to do with that exact sensing capability. So I wanted to make sure I want to keep that crystal clear in front of everybody as we move forward. Okay, so no other questions. We'll go ahead and dive in a little bit. So we
have a question, Bob.
Go ahead.
It's from Nick. And the question is, why do we get a lower ORP when cyanuric acid is in the water?
Mm-hmm.
Why don't we go ahead and answer this question so that we kind of know it's covered? Why do we get a lower ORP when we have a high pH? Make sure we cover that.
We'll talk about that. I have slides that will address all that coming up here.
Cool.
So we're on track. We're good. The only one is the nighttime. I didn't anticipate somebody asking why does ORP go up at night, but we can talk about that. So how does the chlorine generate the ORP value in the water? So basically, we need to go just and again, chemistry was never my fave in school. So, but we need to talk about it a little bit, because to be a good pool person, we have to have some basics of chemistry underneath our belt so we understand why these things happen and how they happen. So when we put chlorine into water, we have two chemicals that are mixing. We have chlorine, no matter what form it is. For our purposes, we're going to keep the equation simple and talk about chlorine gas since it's elemental. It's Cl2. And it makes the equations very simple. Otherwise, if we go to sodium hypochlorite, calcium hypochlorite, or any other forms, then we start to get really some complex looking and unnecessarily cumbersome equations. But we're mixing two chemicals, chlorine and water's a chemical, H2O. So when these two things mix, and that's on the left side of the equation right here, we have chlorine gas added to water, H2O, And what happens is we yield out of the chlorine mixing with the water, HOCl and HCl. This HCl is hydrochloric acid. And just as a side note, this is why when you use gas chlorine in water, you don't use acid as a pH modifier. We have two different acids that are being developed inside the water. So when gas chlorine is used in a swimming pool, not much anymore, but it's just a point of clarity for this, is that we use caustic soda to raise the pH of the water, because the use of chlorine gas in the water drives the pH down. Now, if we use sodium hypochlorite, we know the bleach has a very high pH, and that'll raise the pH, and hence why we have to use acid, or similarly calcium hypochlorite. But again, we're just trying to keep the equation simple. Now, I'm not really too concerned about the HCl. What I really want to pay attention to is the HOCl, or the hypochlorous acid. Now, hypochlorous acid is our, basically, you can call it the active ingredient that's formed when chlorine mixes with water. That's the chemical that's going to be doing the oxidizing for us, and it's going to be doing the sanitizing for us. So when hypochlorous acid is present in the water, it will generate some millivolts. It'll generate potential to oxidize. Now let's take a look at that. If we were to put 1 ppm of chlorine in any volume of distilled water, we're going to get a very, very high millivolt reading. Now, if we put it into swamp water, 1 ppm, we're going to wind up with a very low millivolt reading. Now, why is that? Well, it's simple, because in the distilled water, there's nothing else in the water except just the HOCl. So you have all this potential sitting way high in that high dam lake, ready to go through the hydroelectric dam. Now, if we put the HOCl, we put the chlorine into the swamp water, right away, that hypochlorous acid is being used. It's oxidizing. Once it oxidizes, that HOCl is no longer HOCl, and it's trying to oxidize all those organics. So the potential to do work, it's almost like we drain the dam down very rapidly, and our potential is lower. So in swamp water, when we add the chlorine, we're going to have very low millivolts. Now, what happens if we have HOCl, or the result of chlorine being mixed in water and pool water? What's the millivolt reading then? Well, that depends. That depends on a lot of things. So let's talk about this, and we'll have a few things answered here. So we can call certain things detractors. So the things that in pool water that will lower the millivolt reading in the water is things like organic. That's the swamp water. The lower millivolt is caused by the excess organics in the water. What if we have a very rainy day and we have a lot of runoff that comes into the swimming pool from dirt mounds and grass all the way around? We just introduced a load of organics into the water, and that's going to drop our millivolt reading. Also, if we add cyanuric acid to the water, what we wind up doing with cyanuric acid is actually tying up some of the chlorine capability, some of the potential. And so therefore, the millivolt reading is lowered in the presence of cyanuric. One of the things, as a side note, in the pool industry when adding chemicals, is that there is no free lunch. Every time we add a chemical to the water, or I should say most of the time, there's going to be a desired effect and there's going to be an undesired effect. And that undesired effect is going to have to be mitigated in some way. So that's why when we add cyanuric acid, we don't want 500 part per million of cyanuric acid in the water. You know, more the merrier. It's no different than, well, if I get good effect with taking 2 Tylenol, maybe if I took 20, that'd make me even better. But that's not how it works. And it's the same thing with pool chemistry, is that we want the minimum amount we need to use in order to get the result we want to see. And we can talk more about cyanuric acid a little bit later in the presentation. But I just want to go ahead and talk about the detractors in the pool. Right now, I want to focus in on cyanuric and organics as being detractors. And then we're going to talk about pH in just a moment. I need to go back 1 slide. So how is this all sensed in the water? We're talking, if you have any experience looking at a ORP controller, it typically doesn't say 700 ORP. It says 700 MV, which is millivolts, which is the electrical potential that's generated in the water when the chlorine is added and you get the HOCl. So the higher the potential, the higher the millivolt reading, the more ready the HOCl is to do the work we want it to do. That's picked up by a sensor, an ORP sensor, and we're going to keep this simple too, because I could have one of my engineers come on here who developed these sensors and do a 5-hour presentation of how this all works, but I don't think it serves us any value at this point. But the main thing on an ORP sensor, there will be a platinum tip of some kind. Either it's a little cap that looks like this here, or it's going to be a band going around. Now, as an interesting side note, back in the olden days, the 80s, 90s, when Stranco would put in an order for platinum to make its sensors, it actually would move the value of platinum on the stock market. So I just think that's a crazy little side note, is how it kind of shows you how rare platinum is. The fact that a little company like Stranco out of Bradley, Illinois could move the platinum market by placing a large order for sensors. So it was pretty cool. So basically what we're doing is the HOCl is generating the millivolt in the water. The millivolt's being picked up by the platinum tip here, and it passes through. There's an electrolyte on the inside of here that will go ahead and translate the electricity, the millivolt reading, up into the controller, where it's then converted into a reading for us through the electronics in the controller. It's really important to keep the tip of these sensors clean. Every manufacturer has a set of instructions. Some of them are fairly unique for that manufacturer, and I would just say follow the manufacturer's recommendations. But just like anything, just like a dirty window, you can't see out of it well. A dirty sensor tip is not going to read properly. Or you can think about if you do a wet test and your test tube is stained from leaving your fluid in there, your color change fluid, you're going to have a skewed reading. The same thing happens here. So we have to make sure these tips stay clean. One of the interesting side notes on this, while we're talking about sensors, is that we've seen a major uptick recently within the last 5-6 years of sensors becoming fouled very quickly. And it's due to phosphates in the water. Now, I call this the Flint effect. And I think it's probably etched in our cultural memory now, Flint, Michigan, the situation they had there with water problems. And when they did the water switch at Flint, there wasn't any contamination, or they kept calling the water corrosive and giving people the thought in their head that there's like chemicals in the water that were making it wasn't any of that. Basically, all they did was they switched to a water source that was very low in pH. And so that low pH water tends to leach metals out of the piping. And a lot of the piping in older cities, especially the laterals coming from the water line to the home, excuse me, are made of lead. So lead leaches into the water and makes the water hazardous to drink. There was no like toxic chemical in there causing this. It was just a switch in pH of the water, which they didn't account for. So I think Flint scared a lot of municipalities into becoming overly proactive with their water. So one of the things municipal water systems can do is add polyorthophosphates at the wellhead to sequester the metals in their distribution network. And I think they've gone overboard, my personal feeling, but they did it for a good reason, for people's health, I guess. But the side effect, like I said before, there's no free lunch. The side effect of having all this phosphate all of a sudden in the water now is that sensors are fouling more quickly out of the, within a shorter amount of time. They need more frequent cleaning. And also, as a very unrelated side note, but important one, is that the quartz sleeves on UV systems, especially medium pressure, are becoming fouled much more quickly, and therefore impeding the light transmission into the water and causing nuisance alarms in the UV systems. So one of the things that I encourage people to do nowadays is to also measure the phosphates in your pool water because I've had people reading over 1,000 ppm in their water phosphates, and that's definitely a problem for the performance of a chemical controller, whether it be ORP, your pH value, or ppm. So we need to talk about pH, because pH for me is almost everything in the pool water. Good control of pH is an absolute requirement for good control of ppm if you have a ppm controller, or good control of ORP if you have an ORP controller. Without solid pH control, you can throw that right out the window. Now, I didn't include this as part of the topic that we're talking about today, but I do want to bring it up now, is that as much as pH is an absolute critical factor for accurate control of your water for ORP or ppm standpoint, in order to have solid pH, we have to have solid alkalinity in the water. If we don't have good alkalinity reading in the water, say above 60, below 120, somewhere in that what they call the ideal range, our pH control will be out the window. And if we have bad pH control, we have bad ORP and ppm control. So you can see it's very interrelated, and it's very critical to have good alkalinity, to have good pH, and solid pH is critical before you can have solid chlorine control. So why is this? Why is pH so critical? So let's talk about what pH is first. pH was a concept first introduced in about 1909 by a Danish chemist. This is my favorite definition of all time. It's pH is the negative log of hydrogen concentration, ion concentration in an aqueous solution. So that's a lot of words, basically meaning that you can think of a jug of acid as a jug of hydrogen ions. So the more acid you pour in the water, the more hydrogen ions you're putting into the water, and that forces the pH down. So in kind of basic terms, everyday lingo, we can look and see distilled water is neutral at 7.0. And we can see as you go up the chart to become more basic, we have baking soda, soap, ammonia, and lye. And think about ammonia and lye, especially lye. What do they use in ovens to cut the grease? They use a very caustic product. It's usually up here around pH of 13 or 14. It cuts grease very well. As we move down now, we have normal rain, we have wine, we have lemon juice, we have battery acid all the way down to 0 where acid exists, hydrochloric acid, the muriatic acid that we use in swimming pools, or for some folks, sulfuric acid. One of the things I want to throw out here just for perspective is the pH of your typical colas or any carbonated soft drink is going to be down around 4 or 5 here. Why is that? So I'm not waiting for an answer, I'll just tell you. So it's carbonated. What do they put into the carbon? What's carbonation? How do they do that? That's with CO2. And CO2 is also a pH modifier. A lot of pools in certain parts of the country love CO2 instead of acid as the pH modifier to lower the pH of the water. So you make carbonic acid when you mix CO2 into water. And so that's why the acid content, or why the acidity of soft drinks is way down on this range. If we were to stir the carbonation out of that drink, we'd see the pH go up.
Is CO2 more economical for large aquatic facilities to bring their pH down than using a muriatic acid solution?
Yeah, Lauren, you bring up a great question, and it dovetails into this. It's a little bit separate, but I think it's a good point to talk about this since we're talking about pH and pH modification products. So everybody, the question is, well, do I use acid or CO2? And some folks will say, well, do I use cal hypo or do I use sodium hypochlorite? Do I use bleach, liquid bleach? And I always tell people, as a general rule of thumb, the best product to use is the one that best complements your incoming water to your facility. So for instance, I live in Wisconsin, so we have some limestone formations on the eastern side of the state where incoming water that's just coming out of the wells and then coming through the municipal distribution system has a very high pH and a very high alkalinity. So what I need to do is say, okay, so, and it's a very high calcium content. So what's best complement for that? I really don't want my calcium to go higher than 300 if I don't want it to, or I don't have to let it get there. So I'd probably pick bleach. And since the incoming alkalinity is very high, I would probably choose muriatic acid as the pH modifier to help keep down the effect of any additional fill water that comes in off my autofill in order to complement my incoming water. So that addition of acid not only brings the pH down, but it also drives the alkalinity down. And we need alkalinity in a certain range in order to maintain my pH properly. So you can see the incoming water kind of dictates that. Now let's go out to a mountain region like where they use a lot of surface water, like let's just say Idaho, picking a state at random. So a lot of the incoming water is going to be surface water that's been collected in reservoirs. So that tends to have a low alkalinity and a low calcium hardness. So in those cases, CO2 might be called for because CO2 will modify your pH down from the addition of some chlorine product, but it also brings alkalinity up. And then we may choose calcium hypochlorite because we have a low calcium content in the water. So the calcium hypochlorite leaves behind calcium as a residual to help bolster naturally just through the daily addition the calcium level that's low coming in from that incoming water. So I would say beyond costs, it's actually more smartly driven by the fact is what is my incoming water. Now, if the incoming water is a good pH, if it has a good alkalinity, right, and some places have this, I've seen them go ahead and use both acid and CO2 at the same time, or put it on a manual switch so that when the alkalinity is down, we can add CO2 to bring the alkalinity up. And then if the alkalinity is high, we can switch over and use acid to bring that alkalinity back down. Sometimes you can prevent the addition of baking soda to the water, the bicarb that a lot of people use to have to bring the alkalinity back up once they've used too much acid in the water and brought that alkalinity down below that threshold where we want to keep it, which is above 60 for sure, preferably around 90 to 100. So again, my preference, my recommendation is always to go for what makes the most sense by your incoming water. Now, of course, there's economic concerns there. And some folks can get their bleach delivered dirt cheap because their water utility uses it for the wastewater treatment, and they can roll in all the costs at the pool along with the enormous amount they're using at the wastewater treatment plant to treat that effluent coming out. So primarily, I would say we want to take a look at what the incoming water is and then judge what chemicals we want to use based on that, if it's okay to do that from an economic standpoint. Some people can't get calcium hypochlorite delivery at all. It's too expensive to bring it. Some of the islands, the Bahamas and Caribbean, just cost too much to ship it across by boat. So, but bleach is readily available, so that's something they can use easily. And it's there's some regional reasons why to use one product over another product, but if at all possible, and everything being equal, I would say that's all driven by the incoming water characteristics.
So understanding your source water you fill up with, and would you say especially a smaller body of water like a commercial spa, where that becomes a big factor? I could tell you, we had the county I worked in when I worked for the health department down here. We had most of the county was on county water. Parts were on city water. City water wasn't an issue. The county water that they would fill up spas with specifically, the water coming in had a high pH, and a very low alkalinity. So they were keeping their pH at like an 8 point something, it would be purple, and their alkalinity was like a 16. So what do you do with a situation like that? Because it kind of wreaked havoc on the ORP controllers in our county, because it's like you're using, initially it's set up with liquid chlorine is usually what we see in Florida at least, and then an acid feed. Well, acid feed will take care of the pH, but it's dumping the alkalinity down. And then when autofill kicks on, it dumps the alkalinity down more because the incoming water is 16 alkalinity. So their answer was to add a third feeder on to the ORP controller with a bicarb solution. And that was the only way they could get around it. And believe me, we had our calls with the county, and the county was like, how many commercial spas are we talking about on ORP? Maybe 16. They go, we're not changing our process for 16 commercial spas. So that wasn't going to happen. So it was more of what would you recommend in a situation like that if you had a high pH and a very low alkalinity like that in your incoming source water on a spa?
Yeah, to me, that's a no-brainer for CO2. We just want to make sure it mixes well. I'd use a Venturi feed in it to make sure that the gas is being utilized to its fullest capacity instead of just an injector with a little bubbling stone on it. Get the most bang out of your buck. But I think CO2 is called for each and every time in that situation with a high pH, because again, the CO2 is going to take the pH down while supplementing the alkalinity. And sure, bicarb can help that, but bicarb's going to raise the alkalinity or the pH a little bit too when it gets added. So you're going to kind of fight it against each other there. But I would definitely use CO2 as a route.
That's always a fun, that's the best scenario you'd love to hear for an ORP controller, right? Though, with the source water. It's like
no negative. That's
and you know why we figured out why the alkalinity was so low. pH is high, and then at the very end of their treatment process for their water is a trickle down filter, like a rock filter, and it stripped all the alkalinity out. So
sure.
I had a couple of things in the bots down here. So Clemente had said Northeast US is fairly soft water with low alkaline calcium. CO2 is recommended since it lowers pH and dries up alkalinity, which is what you were saying. And then Corey said, does sulfuric acid affect ORP differently from muriatic acid?
Yeah, so good question. So let's talk about, I'm going to write that down.
And then I just want to say the comment from Clemente was static mixers work wonders on CO2 mixing.
Yes, agreed. Static mixers are wonderful, and I agree 100%. And Venturi feed is a good way too, because it really is a good, the downside on trying to use a Venturi is that you need some type of motive force in order to get the Venturi to work properly. So we need to make sure we get a pressure drop across it, whereas a static mixer doesn't need that. So both are very good solutions depending on the build and the space availability, but agree 100% on that. So going into what is all this talk about pH, and how does it affect an ORP controller, and how does it affect ORP? So if you remember the very simple equation of gas chlorine plus water yields our HOCL plus HCl from the previous slide that we did. Well, more accurately, there's actually a little bit more to this side of the equation. That's why I put these little brackets here, is when this chemical reaction occurs and this is generated, it's generated both HOCl and OCl minus. And these are two different species of this product. This is a molecular side, this is ionic. So this is a pH dependent part of the equation, and I'll show you what I mean by that in a second. So here, if we look at this graph, at a pH of 7.5, the HOCl and the OCl minus exist in about a 50-50 ratio at 7.5 here. 50% of what's formed when the chlorine mixes with the water is HOCl. 50% of it is OCl minus. And now I'm going to get to a critical point after this slide with my next slide, but I do want to mention one thing, and this will kind of dovetail perfectly in here. 7.4 and 7.5 is considered the ideal pH range by many certification classes. Now, in European countries that are covered by the DIN code, their pH, lower pH, can be 6.8. Now, if our ideal range is, and this is going to be rhetorical at this point, why is theirs 6.8 when our ideal range is 7.4 to 7.5? Okay, and I'll answer that in a minute here. So the critical point to take away from here is that HOCl is about 80 times more powerful than OCl minus. So what that means is that the more HOCl is present in the water, the more millivolts we're going to generate. The more OCl minus that's in the water, we're going to have less millivolts. So both HOCl and OCl minus test as free chlorine. So based on a wet test, you're not going to be able to tell the difference. But what we can see is based on this, and this nomograph has been around since probably the 70s, and it's a little confusing. So I'm actually just going to talk instead of showing you that. So let's look at this graph here. As we drive the pH down, let's look at 7. pH is 7, which is neutral. Look at how steep these curves are right within the range of 7, 8, which is, generally speaking, our pool pH range. If we go down to 7, look at the HOCl right here. It's about 75, almost 80% HOCl here. We're going to have a lot more millivolt generated from the same quantity of chlorine at a lower pH. As our pH goes up, we can see the HOCl species kind of goes away, and the OCl, the less powerful form, becomes the predominant species. Where at about here at 8, we see about 75% is the OCl minus, and that's not desirable. So this simple little graph shows you why when the pH of the water goes down, we have more millivolt, and why when the pH goes up, we have less millivolt in the water. It's just because of this exchange of species, and it's totally pH dependent. Doesn't depend on anything else except just pH. This is why the ideal range is 7.4, 7.5. Some people that I know that run water parks like 7.2. They keep it right at the bottom. Why is that? That's because they know they can get the most bang out of their buck of the chlorine. They have the most oxidizing and sanitation potential at a lower pH than they do at a higher pH. So why do the Germans keep 6.8? Well, they require the most bang out of their buck possible because they limit their chlorine content in the water to 0.6 ppm. Now, I'm not going to go into the reasons why they do that, but knowing that they have the quantity of chlorine lower in the pool, they need to make sure that small quantity is working as hard as it possibly can, so they allow the pH to be lower. We in the United States, depending on whatever state you're in, you could have 3, 5, some people are fine with 6, 7, 8 ppm in the water. They don't care. Germans come over and think we're insane because they call it, even their tap water, they can barely stand because of all the chloramine in the water, and they're getting doused, and they're very sensitive to that. They're not used to it like we are. But this is why pH control is so critical in a controller. Because if we don't have control of the pH, if this pH of the water is flying all over the place, which it can with the low alkalinity, then the ORP value is going to be flying all over the place. And therefore, we're going to have feed events and no feed events and feed events and no feed events. We're going to drive the controller crazy, and eventually we'll probably get an alarm out of it. So this is why stable alkalinity, stable pH is a requirement for stable ORP control in the pool. Notice I didn't say stable chlorine content. I said stable ORP. So we're going to talk about that in just a minute here. So some key takeaways here, and we can go in to answer some of these questions, is that ORP is a qualitative measurement of the water, what's in the water, our chemical, our HOCL, its potential to do work. ppm is simply a quantitative measurement. It tells us nothing about if the chlorine's ready to work or not, if it's tied up by cyanuric, if it's being used up by a heavy organic load, if it's being sucked up by sunlight, whatever it may be. So if the pH changes, the ORP value changes. And if there's anything we take out of this presentation today, is that ORP controllers control ORP. They do not control ppm, because there's so many different variables that can go ahead and change the ORP value, that we're just trying to control ORP. And I remember a long time ago, one of the engineers at Stranco, when I was there, said that, for instance, this is a great illustration of how an ORP controller works, or the way an ORP controller looks at the world, is that the proper response for heavy organic loading in a pool utilizing an ORP controller is more chlorine, because it's trying to hold an ORP value, not a ppm value. Some of the more sophisticated controllers you'll find on the market right now actually look at both ORP and look at ppm, because we do know that ORP is a very valuable measurement. But if we look at health department requirements, very few states require any type of ORP monitoring or control or value being held. All the code requirements wrap themselves around ppm, around the quantity of the water. So one of the things, if you do have an ORP controller, is do not drive yourself crazy by saying, my controller will not hold 2 ppm. Well, it's an ORP controller. It's not designed to do that. You'll see your ppm vary because it's trying to hold an ORP value, not a ppm value. And any nomograph that's developed in the laboratory, like this one, is not an accurate representation of a chlorine content versus pH of what you're going to get into the water, because there's other variables that are not accounted for on a nomograph like this. So we can answer some of the questions now that were part of our parking lot here, and then we can also open the floor up to further questions. So one of the questions is, why does cyanuric acid lower the ORP in the pool? The cyanuric acid, basically, it's a protection from sunlight, from losing chlorine to the effects of UV radiation. So by doing so, we actually inhibit the chlorine's action. We protect it from being destroyed by the sunlight. So when we inhibit it like that, or protect it, or put a casing around it, a shell, then it doesn't become as active and doesn't generate as much ORP value. This is why some of the largest water parks in the country do not allow cyanuric acid in their water, even though they're in Florida. They just will spend the extra money. Now, as a controller manufacturer, am I against cyanuric acid? Absolutely not, because some facilities cannot survive without adding some cyanuric acid to the water. However, I would caution everybody is that at 20 part per million roughly of cyanuric acid in the water, you're getting pretty much 80% of the savings that you're going to get out of the use of that chemical, and any additional quantity over 20 ppm is only going to detract from your capability to oxidize, to make the water look sparkling, and then also disinfect. And you will see hundreds of studies online, if you ever want to spend the time to go in and see the negative effect that cyanuric acid has on disinfection capabilities. CDC put out some great ones with cryptosporidium about 5-6 years ago that are available. Now, the other question is sulfuric acid versus hydrochloric acid. A lot of this has to do with the purity of the acid. Unfortunately, some of the acids that we get in the pool industry are basically used in other processes. And so there's a lot of junk that gets delivered along with the acid that you're getting. You want to make sure that your acid that you're getting is pretty pure and doesn't have metals in it or any other contamination. As the difference between sulfuric and muriatic or hydrochloric acid, same thing, for all practical purposes, they're going to work just as well and have the same effect, roughly at the same quantity, because they're both very, very low pH, effectively 0. We just want to watch about contaminants going in there. And of course, sulfuric doesn't fume like the hydrochloric does, so there is a slight benefit there. Why does ORP go up at night? So I think, did I answer that question already with why we add cyanuric acid? Because we don't have the sunlight degrading the chlorine. It's that would be my guess. I don't see, maybe there's a difference in organic loading. Maybe nobody's getting in the pool at night. I don't know if the pool's open at night or not. But if we take away some of the contamination and we take away the effect of the sunlight, then what we do is we free up the chlorine that's in the pool, and it's going to generate more millivolt for us. So generally speaking, it's going to be a removal of things, of being UV radiation, and the removal of people getting in the pool. Because can you imagine, with nowadays, with all the modern chemicals we put on our body and we put in our body, that come out of our sweat, that's on the lotions, the suntan lotions, maybe makeup, antiperspirants, deodorants, all that goes into the pool, and that puts a demand on the chlorine. Because at any of the water parks nowadays, or most pools, nobody's showering before they get in anymore. Not like it used to be back in the old days. And it's certainly not like Germany, where everybody has a cultural ingrain that before I go in the pool, I will shower with soap and water. And then I have to be clean before I get into the pool. Some people exercise, they just got done with like a 5-6 mile run and lifting weights maybe, and they dive into the pool to refresh themselves. And all that stuff that's been sweating out of their body goes into the pool and puts a demand on it. Or we also know that we have giant water parks with maybe one bathroom that's, 300 yards away. No kid's going to get out and stop playing, so we have people using the pool as a giant bathroom too. So hopefully that answers that question. So I guess we can open up the floor, Lauren, at this point, and see if anybody has any questions. And
so if there's anybody watching on Facebook Live, I have the chat window open. You can certainly just type in through your Facebook there any questions you might have that you're listening on. Anybody here have any questions, come off mute or use the chat window. Give people a couple of minutes to respond. So at night, if they have a pool cover on the pool, that would certainly probably help with less contamination, Bob, and then you'd have probably a higher ORP level.
Possibly, yeah. One of the things with putting a pool cover on, especially outdoors, is we stop evaporation. Evaporation will save on heating energy bills. Because of evaporation, we lose a lot of heat energy through the evaporation process. Certainly keep organics out at night because the pool's being covered. Now, one of the things that may happen, if it's a solid cover, it's a bubble cover, that type of thing, or some type of non-breathable surface, we might be, and it gets a little complicated, but we might be stifling chemical reactions from reaching completion in the water, because we can't get the off-gassing of some of the products that are released. So we tend to slow the chemical reactions from completion in the water down. And there's a certain sequence of operations as chlorine oxidizes products, because the chemistry I showed you is awfully simple, and there's so many chemical processes occurring in the water that we don't really have them all quantitated or quantified. So there's things, chemistry happening in the pools we're really not 100% aware of, because all the organics, all the millions of different things that are going into the pool on a daily basis that react with chlorine, we haven't studied every single one of those. We don't know. There's things happening that we just don't have the money or the time or the capability or the need really to go in and see all these reactions. So long story short, on a pool that has a cover on it, we may see some of those chemical reactions stifled a little bit until it becomes uncovered again. And on an indoor pool, that could lead to some chloramine buildup in the water if you don't have another supplemental system like UV taking care of it on the treatment side.
All right, anybody else have any other questions? All right, well, I guess nobody has any questions. Oh, wait. Are there any ORP, this is for Clemente. He said, are there any ORP points that have a benefit to a pool?
ORP. Could I get a clarity?
Are you able to come off mute or use the chat window to give us a little bit more clarity, Clemente?
Yeah, sure. No, I just wanted to know if he was aware, or does he know of any ORP set points that a facility can maintain to get a specific benefit?
Oh, I see. So yeah, that opens up a whole can of worms. So before I answer that question fully, and I got to talk a little bit about history behind that. So using, and this is probably one thing I probably should have mentioned in the presentation, is typically the way we set up ORP controllers to try to do the best we can to maintain a ppm value, something close, is we'll go ahead and take a a pool that's quiescent. It's not loaded right at the point. Maybe in the evening we're taking a measurement, and it's like best case scenario we're thinking, maybe like a freshly filled pool or whatnot. And then we go ahead and hand dose the pool to make sure that the alkalinity is exactly what we like, that the pH is exactly what we want, and the ppm value is exactly what we want. And then we go ahead and measure, take a note of what that millivolt reading is, and then we go ahead and make that the set point. And so then we're guaranteed that we have, when a pool gets really clean, we can generate a lot of millivolts with very little chlorine in the pool that may not be in keeping with what the local code requires or the state code requires. So that's why we want to get the ppm value in the water, guaranteeing that once we organic load it, it's going to just only go up from there. And it may oscillate a little bit, but that's how we set up try to set an ORP set point value. Now, going back what you're talking about, Clemente, and correct me if I'm wrong, but a long time ago, there's a school of thought developed. It was called continuous breakpoint chlorination or halogenation, where that if you had a certain millivolt value in the water, it's always going to be keeping the water clean and also destroying chloramines. And we see some people still moving forward with that concept. Honestly, I don't think it's that simple, that if you just tell somebody you hold 800 in the water, you're always going to have a way better water than you will at 750, because then we start getting into the chlorine content of the water. And what if it takes us 8 ppm to hold 800? Then we wind up causing some headaches with the local health officials in a lot of places. So I don't have a recommendation for a minimum millivolt to see that kind of benefit. I mean, I certainly don't recommend anybody going under 700, because we do know that a lot of disinfection capability doesn't work real well below 650. 700 is kind of, in my mind, at least on our controllers, that's our factory default for an ORP set point. For some of our controllers that control ORP and ppm together, our set point for our normal ORP controllers is about 740, if I'm not mistaken, or 750. One of those two is the factory default, but then it's just adjusted per taste based on what the water constituent makes the ORP generate at. Have you seen anything that you say you notice a huge difference as somebody keeps this value versus this value in the water?
Actually, my contention on ORP control is that the sizing of the chemical feeders is a big issue. I find that robustly sizing your chlorinator giving your controller the ability to meet pretty much any demand is more important than the set point. But what I have found is if you have a big enough feeder in the connected to that controller, you can actually reach that point where chloramines are not being produced in the pool, and higher ORPs, like you said, are maintaining a lower parts per million. And yes, and at that point, what I tend to do is I tend to maintain an ORP level that establishes a minimum amount of chlorine, such as a 1 or a 1.5, just to keep for health department, and then let it run. And like you said, it'll fluctuate throughout the day. But yeah, I have pools in New York City that absolutely have no smell, and their UVs are actually shut off because they have a robust feeder that's putting in quite a bit of chlorine, but their chlorine value never gets above a 2. So
yeah, Clemente, you bring up just an excellent point. With automation, with controllers, large feeders are required in order to meet set point quickly. The last thing you want to do is have an undersized feeder struggle to reach set point throughout the day, especially when they're heavily loaded, because you do get in a vicious cycle then is you can't keep up with the organic loading in the pool, and you're just feeding all day. And what you wind up seeing people with undersized feeders like that is they'll go ahead and maybe adjust the ORP value, the set point during the day, and then have to go back in and turn it down at night. And then you may see alarms kicking off when they have their fail-safe alarms kicking off after a 6-hour feed and they're not reaching set point. And so, no, I can't agree more than you have to have those feeders properly sized at the get-go in order to meet set point as quickly as possible. And ideally, we want millivolts as high as possible, like you just said too, with the lowest ppm possible. That's the Germans' contention, is they know, we know, but we just don't talk about it too much. And you can talk to Dr. Michael Beach about this, but he's been wrapped up with coronavirus right now down at the CDC. But he goes, they know disinfection byproducts are a problem.
Yes.
And but it's just something that just, I think they're scared to talk about, because that's a can of worms to open up that no, you know, I mean, what do you do?
Well, I mean, companies like what is it, the Pulsar feeder, they've done some studies because they're very interested in seeing the model health code change its requirements for chlorinator sizing, because that's according to the numbers that are on the current mock, those numbers are too low. And they actually did a study, and the results of the study proved that their feeder sizing was too small too. So that's led them to build feeders that put out more output, and they're hoping that I guess the next mock meeting they'll finally establish a better sizing parameter.
Yeah, and that's a good point too. And one of the things I haven't done yet, I know Florida has a feeder sizing requirement built into code. So does the state of Illinois. And I know a lot of design firms, some of the bigger engineering firms utilize either Florida or Illinois, which is, they're very big, the feeders for per gallon per minute. And I think Lauren can speak on the Florida code very well, having firsthand experience with that.
Yep, our millivolt reading, am I off mute? Yes. Our millivolt reading down here is 700 to 850 millivolts.
How about chlorinator sizing? Like, how big does the chlorinator need to be for the pool?
So they have to be able to get 6 parts per million into the return flow. So the output rate needs to meet that. And then storage capacity of the chemical on site has to be 50% basically of the maximum output rate of the feeder.
Yeah,
and that's one thing I haven't done, Clemente, is just and that's something interesting I'm going to do when I get off the call here, is just compared what the current MAC is compared to the state of Florida and state of Illinois requirements. To see, I'm just curious. It's just, it'd be nice to have that all standardized in the very right way.
Right.
Yeah,
It's like New York.
there's a calculation that I have. You take if you have like down here in Florida for commercial to figure out proper output rate for a pool. And I've been told it's the same calculation if it's for gallons or for pounds per day or gallons per day. It's like taking the design flow rate of the pool from the engineer and you divide it by this conversion factor they have, which was developed from that whole 6 ppm required into the return flow. We could do a whole class just on that, just for Florida.
Yeah, Lauren, real quick, that's more for it'll get you towards the minimum sizing. So you always take that as your lowest standpoint, and then you actually have to always put it size it higher than that, or else you're never going to keep up with the bathing load. I've already done that test.
Especially, well, and that's what they always said is especially a commercial public spa, because you're heating the water up, it's gonna, you get a lot more contaminants in the water. So you always want to upsize that from the 6 ppm, especially in a commercial spa situation, to account for that you don't get on a swimming pool.
Yeah, that's something I always tell everybody, that when they look at their state codes, because there are several states that actually have a sizing parameter, but everyone thinks that's law, that's it. No, it's a minimum standard. You can go higher than that. So the one I like, my favorite funny one is New York State, that tells you that a chlorinator needs to be able to achieve 10 parts per million. But it doesn't tell you how fast it's supposed to be. So you could have two bids, and one guy will have one pool bid for a pump that goes to 10 parts per million in an hour. The other guy is going to do his in 6 hours, and because that pump is smaller, the pump is, that system is going to be a little cheaper, and they'll end up winning the bid. So those are
that's mainly how Florida is set up, mainly the same way, where it's it doesn't matter the time frame, it just needs to be able to accomplish that within about 24 hours, which is ridiculous.
Yeah, it's
always set the size way higher than whatever they have it as.
Yeah, no, one of the things that gave me that attention in terms of that is the fact that in New York State, back in the late 1990s, I was able to see 3 of the original Strantrol 311B installations. Nice. with the original Wallace and Tiernan pumps that they came with. And I noticed that those pumps were big. And towards the 90s, you started seeing these installs with much smaller pumps. And then people started having problems with the chloramination. And I think I was trying to figure it out, and I think I figured it out why that happened. But everybody, once the controllers started, once controller manufacturers started popping up, and Strantrol was no longer the only guy in town, everybody had to dummy down their pumps to try to win a bid. And eventually, even Strantrol started dropping their pump sizing parameters. And unfortunately, chlorinator sizing was never set in stone from the beginning, so that engineers can say, hey, the pump should be really this big. So yeah, so those old systems, which I think today only one still operates, which is amazing. Their pumps are like can achieve, I think, 15 parts per million in 1 hour. So, and they're still keeping that pool perfect. That's all I got.
Okay, right. Those are excellent comments. Thank you.
You're welcome.
Thank you so much, Clemente.
So I put up my slide here with my contact information in case anybody would like to reach me. Feel free to call or email.
Yep, and this will be up on the recording too, so you may get some emails after the fact.
Happy to answer them. Or I'll just, actually what I'll do is I'll shuffle them off to Conan or John. So.
Oh, learning experience here. See, they can answer the question.
That's
They-
right.
They're good. All
Hey,
right, well,
Bob,
yeah, there we go.
were you able to answer the ORP at nighttime, the difference?
Yes, he did
Yeah.
that earlier. But go ahead again, Bob.
Okay.
Yeah, sure. So my guess, I've heard this maybe one other time that people see this effect, and my guess would be the fact that at nighttime we see ORP values go up because the filter is able to catch up with organic loading. It's able to get a few turnovers in there. We're able to clean up the pool so that the chlorine doesn't have to do some of the work. Some of the work is being taken away from the chlorine and being captured by the filter. We're no longer putting people in the pool so that the organic loading is gone. And so then the filters can go ahead and filter out more of the material that normally would be reacting. Also, we don't have any more sunlight, which is going to be hitting the chlorine and dropping the ORP value. So those are the two things that I would think about as at nighttime, that we just don't have the organic loading occurring with people in the water as much. And it would be interesting to me to see if there is a nighttime pool where more people are in at night during the day, if we still had the same effect, that even at night it would still go down. And I'm assuming that when you say at night too, this is an outdoor pool, not a
Correct.
indoor pool. So also obviously no sunlight, so we see less UV radiation attacking the chlorine in that way. Now, if we had feeders that were really big, we might be able to see, the ORP value stay pretty static. But typically what we see is during the day with heavy loading, we see sunlight, and we a lot of people in the pool making the organic loading, is we see feeders that may struggle to keep up. So I think this really speaks towards Clemente's comment, which is spot on, is that we need feeders that can respond either at night or during the day to our demands for chlorine and not take the time to get to set point. I think if it takes us 2 hours to get to set point, that's unacceptable. I think we need to be able to hit set point within a half hour to an hour.
Perfect. Thank you.
You're welcome.
All right.
Would you recommend enzymes in the pool to help out with the ORPs?
Yeah, I mean, as long as it's high quality enzyme, and that's a great question, Corey. As long as it's high quality and proven effective, has a good reputation. I've heard some very, very good things about enzymes in the pool, helping as to keep organics out, break down more complex organics that chlorine can't take care of, and also helping break down some of the biofilms that chlorine has a hard time with too, because chlorine isn't perfect. I mean, it's been said that chlorine is the most important advent of the 20th century for public health, because it's made our drinking water system safe. And same thing with pools. I don't think there's a better product we have right now that you can leave as a residual in the pool and do all the things that it does at the cost that it does. I mean, we obviously can't put ozone in a residual in the pool. Bromine certainly doesn't work as well as chlorine as a residual in the pool. So if we have something that's complementary to the chlorine and help free it up to do more of what it's supposed to do, we could probably wind up using less chlorine overall. Now, does that work from a cost standpoint? I don't know how expensive the enzyme is or how much you need to use. So there's definitely a cost benefit that would need to be looked at, do an analysis on that. But back to your question, to keep it simple, I know some people that have seen some very good things with the enzymes. I do know the enzymes will help keep our sensors cleaner, will help keep UV lamp sleeves cleaner, but I don't think it's going to help against phosphates. That's something different.
I've
But that's
seen
a good
one. I've
question.
seen one ORP controller down here in Florida that we had on one of our public pools, where they had another Stenner pump that was feeding like an enzyme type thing that was gonna, or it was like a cleaner to be able to keep the probes clean. and they had a little jug down below, and I've seen the enzymes fed before. What about phosphate removers? That would certainly help too, because you talked about phosphates building up on the tips and stuff, so that would be good as well. I would just
It's a
say, like,
requirement. Yeah.
as Clemente said earlier, check your state local health code if you're dealing with public pools. Make sure any of these specialty chemicals you're using, if the state code says they have to be NSF approved, that they're NSF approved before you add them to the water, because that's what the health departments are looking for in most instances. But otherwise, they assist the chlorine so that it's not having to do all that oxidation. It can disinfect, and then the enzymes are helping to break down some of the other stuff in the water, like, body lotions and sunscreen and all that stuff. It helps break that down so that it's not trying to oxidize and disinfect at the same time, is my understanding, is the benefits of enzymes.
100%.
Thank you. And then another one, which one has a bigger effect on ORP, TDS levels or phosphate levels?
So many years ago, probably during the 80s, maybe 90s, there's a guy, anybody ever heard the name Kent Williams?
Yes.
Yes.
Okay, so those of you that have had the pleasure of knowing Kent, Kent and I, at one point, we were very good friends. I don't see him very much anymore, but he wrote a really good paper that's called "What's the Fuss About TDS?" I can make sure that you can find it on the internet pretty readily. It's called "What's the Fuss About?" or "What's All the Fuss About TDS?" And it really breaks it down in layman's terms. And Clemente, Lauren, you might have some other opinions, but I don't see high TDS having a very important effect on ORP values. We're talking about total dissolved solids. So typically dissolved solids are going to be metallic elements in the water. It's going to be sodium, it's going to be calcium, magnesium. So it's dissolved. We're not seeing a clarity issue with dissolved solids because they're dissolved. And I really don't see, sodium's going to change the conductivity of the water, which in turn is going to change the way the millivolts transmit through the water. But I don't see, a lot of people say high TDS is going to make my water cloudy, or high TDS is going to affect my ORP value in a very negative way. I don't see it being that important under normal everyday pool conditions. Now, certainly there's going to be some extremes out there where you have just sky high TDS, but then we got other issues we have to deal with. So you were asking between TDS and phosphates. The phosphates themselves are going to cause a problem because they're impeding, they're going to coat the tip of your sensor and impede the proper reading. Phosphate in the water, as a general rule, isn't going to be a problem for millivolts to be transmitted. It's just going to be the effect that they have on impeding the proper function of the sensor, which I guess you could say phosphates are a problem then, but it's not because they're in the water, it's because they plate on the sensor.
Which they do the same thing to salt chlorine generators.
Mm-hmm.
They
Mm-hmm.
basically coat the blades of the salt chlorine generator, and it impedes it making chlorine.
Agreed. The only thing I could say about TDS is, and I've seen this a lot, is if you let the TDS go up way too high, it does affect your water balance. As a matter of fact, the PHTA just changed their calculation guidelines for the LSI calculation. They actually have factors now for TDS up to 5,500 parts per million.
Pools.
For pools. And I've seen pools that have gotten up to about 8,000 parts per million. And I've had to ask the customer to dump, because at 8,000 parts per million, I can't tell you the composition of the TDS, but their DPD test came out orange instead of pink. So how can they test the amount of chlorine that's in the pool if it's turning a different color? So especially with these regenerative filters, they have a problem with TDS going up because since they're saving water by not backwashing, their TDS goes up quite a lot faster. And what ends up happening is that they end up breaking their promise of water savings because now they have to dump that water. And I know one pool in particular, one facility in particular in Connecticut, they have two 18,000 gallon bodies of water. One is a training pool and the other is an interactive pool with a water slide. And every 3 months, they have to dump 36,000 gallons of water to be able to operate properly. And the owners of that facility were not very happy with that advent because they were expecting a huge water savings. The good news is that their main pool, which is a 800,000 gallon Olympic pool, they haven't had the need to drain that pool for what, 6 years now. The TDS is still staying relatively low because they're not getting the equivalent bather load that those two smaller pools are getting.
And I was going to say the same thing as I always saw TDS affecting ORP mostly on like a commercial spa, smaller body of water. It seemed to have a quick, more of an effect on how it operated than a swimming pool on an ORP system. And I think it largely had to do with water balance more than anything else.
Mm-hmm.
Agreed with that. And just consider the fact that ORP controllers are used on seawater aquariums where the TDS in the water is 35,000.
Exactly.
So, so the TDS is not going to like hamper the performance. You just have to take it into account. And I agree with the water balance from a standpoint of the LSI. And also, I don't know the interference that a high TDS would have on a test kit. I'm not within my area of expertise, but there's a lot of things in the water that do have interference with proper wet tests. Mm-hmm. And I'm sure, Lauren, if you haven't already, maybe bringing somebody in, I can make some recommendations from some people that would be really good to talk about interferences with wet test kits, one of the manufacturers that would in a heartbeat come on and help you out with the presentation like I did with ORP.
Awesome. All right, any other questions?
Good stuff, people. Thank you.
Yeah, had some good conversation. Thank you. Thank you for being on today, Bob.
You're welcome. My pleasure. Happy to help out.
It's been a pleasure as well. Thank you so much, everybody, for being on today. All right.